I was standing in my kitchen this morning, just staring at the salt shaker.
A very philosophical start to the day.
Well, it was actually,
Yeah.
because I was thinking about what we were going to cover today, and I'm looking at this salt, this, tiny crystal,
Right.
and I'm thinking roughly half of this little thing is sodium, which is a metal that literally explodes if you so much as touch it with water.
Explodes, yeah.
Violently.
And then the other half is chlorine, which is this deadly poisonous gas. I mean, they used it as a weapon in World War I.
What a terrible weapon.
And yet you put them together on your fries, and it's delicious.
It's delicious. It's essential for life even. It's wild.
It's completely wild. And that's really what we're doing today, isn't it? We are looking at the ingredients of everything. We are doing a comprehensive deep dive into the periodic table.
The ultimate recipe book of the universe. The ingredient list for reality.
And I want to be really clear right off the bat. This is not going to be a high school chemistry flashback.
Oh, please no. You don't have to sit there memorizing abbreviations or, worrying about a pop quiz.
No, that's the quickest way to kill curiosity. Our goal here is to understand the story.
Exactly. This is about zooming out way, way out to something like the Crab Nebula, and then zooming way, way in, past your skin, past your cells, right down to the atomic level.
Right.
We want to understand the personalities of the building blocks that make up our entire reality.
And personalities is really the right word, too. I love that word for this. Because when you actually dig into the sources, you realize these elements, they aren't just static things sitting on a chart in a science lab.
Not at all.
They act in very specific, sometimes very dramatic ways. Some are, aggressive and desperate to react. Some are solitary loners that don't interact with anyone.
And noble gases.
And noble gases, yeah. And some are the sturdy builders that literally hold our civilization together. It's this fascinating cast of characters.
So let's start with the absolute basics, the definition. When we say element, we are not talking about earth, wind, and fire anymore, are we?
No, definitely not. Though it was a great band.
It's true.
But yeah, that was the classical view. And it makes sense, intuitively, if you put yourself in the shoes of someone living 2,000 years ago.
Sure.
You look around the ancient world, and what do you see? You see solids, that's earth. You see liquids, that's water. You see gases, that's air. And you see energy or heat, that's fire. It was a poetic way to organize reality based on what you could feel and see.
It had a certain logic to it, for sure. Hot and dry meant fire, cold and wet meant water.
Exactly. But it wasn't chemical. It couldn't explain how things actually reacted or, changed from one substance to another. Today, thanks to modern science, we know that an element is something much more specific, much more rigid.
So give us the modern definition. What's the bedrock?
An element is a substance that cannot be refined or purified into simpler ingredients. It is the absolute bottom line.
The fundamental thing.
The fundamental thing. If you have a bar of pure gold and you cut it in half, you have two smaller pieces of gold.
Still gold.
Right. If you keep cutting it down and down until you have a single atom of gold, it's still gold. But if you try to cut that atom,
Stops being gold.
it stops being gold. You've broken the fundamental identity of the substance. You've got protons and electrons, but you don't have gold anymore.
So it's the smallest possible unit of identity for a substance.
Correct. And instead of the classical 4, we now know of at least 118 of them.
Wow. So our mission today is to unpack this recipe book. We're going to look at the history of how we even figure this out, which is a detective story in and of itself.
Oh, it really is.
How the table works, and then we are going to dive into the specific families. Because, and this surprised me a lot in the research, the layout of the table isn't random at all. It's a map.
It is absolutely a map. And once you know how to read it, you can predict how the universe behaves. It's like having a cheat sheet for reality.
I love that. A cheat sheet for reality.
Yeah.
Okay, let's unpack this. Before we can even get to the table itself, we have to understand the brick. We have to look at the atom.
The fundamental unit. Yes.
This was the part of the research that always just breaks my brain a little bit, the sheer scale of it all.
It's impossible to visualize comfortably, I think, for the human mind, but we have to try. So you have the atom, and inside, it's not just a solid ball, like a little marble.
Right.
It's a complex little solar system. You have a trinity of particles you really need to know. Protons, neutrons, and electrons.
Okay, let's break those down. Who goes where and what do they do?
Okay, so let's start in the dead center, the very heart of it. You have the nucleus, this is the heavy core, and packed tightly inside there are the protons and the neutrons.
And the protons are the VIPs here, right? They're the important ones.
They are. The proton defines the element's identity. We call this the atomic number, and this is the rule that cannot be broken.
Okay.
If an atom has one proton, it is hydrogen. Period. End of story. It doesn't matter what else it has. One proton means hydrogen.
So if it has 8 protons.
It is oxygen, always. If you could somehow magically shove another proton in there so it has 9, it instantly stops being oxygen and it becomes fluorine. It's a completely different substance.
So the proton count is like the DNA or the, I don't know, the social security number of the element.
That's a great way to put it. It's the unique identifier. And they also have a positive electrical charge. That's important.
Okay, so protons are the identity, positive charge. What about the neutrons? They're also in the nucleus, right? Squeezed in there.
Right. Neutrons are sitting right next to the protons. They have no charge. They're neutral, hence the name.
So, or are they just filler, just dead weight?
Not just weight, though they do add that. Think of them as the stabilizers. Or maybe the peacemakers.
Peacemakers, how so?
Well, protons are all positively charged, right? And what happens when you try to push two positive ends of a magnet together?
They repel. They push each other away hard.
A violent repulsion. So if you just shoved a bunch of positively charged protons together in a tiny nucleus without anything else, they would fly apart instantly. The nucleus would just explode.
Oh, yeah.
The neutrons act as the buffer. They're like the packing peanuts or the glue that allows those protons to cluster together without repelling each other into oblivion. Their main job is stability.
So that's the heavy center,
Yeah.
the nucleus. And then you have the electrons way out on the fringes.
The busybodies. I like to think of them as the busybodies. The electrons are orbiting around the nucleus in layers, which we call shells.
And these guys are tiny.
Incredibly tiny, about 2,000 times smaller than a proton. They have a negative charge, which is what keeps them attracted to the positive nucleus.
These are the ones that actually do all the work in chemistry, right? This is where the action happens.
Precisely. The nucleus just sits there, providing the weight and the identity, like a CEO in a corner office. But the electrons, specifically the ones in the outermost shell, they are the workforce. They're the sales team. They're the ones reaching out, bumping into other atoms and making connections or breaking them. When we talk about fire or rust or digestion, we are just talking about electrons swapping places.
Here's the thing that always blows my mind about atomic structure. We talk about the nucleus and the shells, but the scale is just. It doesn't make any sense to the human brain.
It creates a real paradox because almost all of an atom's weight, like 99.9% of it, is packed inside that tiny nucleus. But the nucleus itself is 100,000 times smaller than the atom as a whole.
The analogy in the reading was a football stadium.
Hmm.
We use that?
Yes, let's use that. It's the best one I've ever heard. Imagine a massive professional football stadium. The Superdome, maybe?
Okay, huge place.
The nucleus, that heavy core with all the mass, would be a single marble. A single glass marble sitting on the 50-yard line.
A marble. That's it.
That is it. And the electrons, they would be tiny gnats or maybe dust motes buzzing around the very, very top row of the nosebleed seats.
And everything in between the marble on the field and the gnats in the top row.
Empty space. Nothing. Absolutely nothing.
That is wild. Most of everything is just empty space.
Which implies that everything you touch, the table in front of you, your phone, the chair you're sitting on, even your own face, is 99.9999% empty space.
So why doesn't my hand just pass right through the table? If it's all empty space, why is anything solid?
Forces. It all comes down to forces. Specifically, electromagnetic repulsion.
Okay, break that down.
The electrons in the atoms of your hand are negatively charged. The electrons in the atoms of the table are also negatively charged. As your hand gets close, those two sets of negative charges push against each other with incredible force.
Like the magnets again.
Exactly like the magnets.
Yeah.
You aren't actually touching the table in a physical sense. You're hovering microscopically above it, suspended by invisible force fields.
That feels deeply existential. It feels like a glitch in the simulation.
Welcome to atomic physics. It gets weirder the deeper you go, believe me.
I want to circle back to something you mentioned, the neutrons. You said they add weight.
Oh.
Does the number of neutrons ever change the element?
No, and this is a really crucial distinction. The proton count defines the element, that's the law. But the neutron count can vary.
Okay.
When you have the same element but with a different number of neutrons, we call those isotopes.
Can you give us a real-world example of that?
Hydrogen is the classic example. A standard run-of-the-mill hydrogen atom has 1 proton and 0 neutrons. That's it. Simple.
The simplest thing.
The simplest thing. But there is a form of hydrogen called deuterium. And deuterium is just hydrogen with one neutron. And there's another one, tritium, which has two neutrons.
But they're all still hydrogen. They all act like it.
Yes, because they all have just one proton. Chemically, they act like hydrogen. They'll bond with oxygen to make water, for instance. But physically, they are heavier.
So you can have heavy water.
You can. Heavy water is actually just water made with deuterium instead of regular hydrogen. It's used in nuclear reactors and scientific research. It looks the same, but it's about 10% denser.
Okay, so that's the brick. That's the atom. Now let's talk about the house, us.
The human collection of elements.
Yeah, I think it's so easy to think of elements as things in a lab, chunks of metal or beakers of gas. But we are just walking, talking collections of these elements.
We absolutely are. The human body uses about 60 different elements, believe it or not, but it's not an even split at all. There are what scientists call the big six that make up 99% of your body weight.
99%. Okay, run me through the big six. Who am I really on a chemical level?
Okay, well, number one, the biggest by far is oxygen at roughly 65%.
65%. I'm 65% oxygen. I feel like I should be a slightly solidified
But
cloud.
mostly you are water, right? H2O. And water is mostly oxygen by weight. So yes, you are mostly oxygen.
Okay, that makes sense. What's next?
Next up is carbon at around 18.5%. That's the structural backbone of, well, everything important. All your cells, your DNA, your proteins. Life as we know it is carbon-based for a reason.
So oxygen and carbon are the big hitters.
They're the heavyweights. Then you've got hydrogen at 10%, nitrogen at 3%, calcium at 1.5%. That's almost all in your bones and teeth.
Right.
And finally, phosphorus at 1%.
And that's it. That's 99% of me right there. Just those 6 things.
That's you. The remaining 1% is a fascinating mix of trace elements, things like potassium, sulfur, sodium, chlorine, magnesium.
It sounds so insignificant when you say trace elements, 1%.
But don't let that small percentage fool you.
Yeah.
They are absolutely vital. You would die almost instantly without them.
How so?
Well, potassium keeps your heart beating on a regular rhythm. Sodium allows your nerves to fire signals to your brain and muscles. They are the spark plugs of the biological machine.
It's humbling, isn't it? We are just a temporary, very specific arrangement of oxygen, carbon, and a pinch of salt.
In a way, yes. A very complex and beautiful arrangement, but an arrangement nonetheless.
So we have all these elements, 118 of them. How did we go from earth, wind, and fire to this beautifully organized chart we see in classrooms today? Because that did not happen overnight.
No, it was a centuries-long puzzle. It was a huge international effort. You have to imagine scientists finding hundreds of puzzle pieces scattered in a box with no picture on the lid.
That's a great image.
That's where they were in the 18th and 19th centuries. They were just trying to organize the chaos.
Who started putting the first pieces together?
One of the first really big attempts was by a French scientist, Antoine Lavoisier, back in 1789.
Okay, right around the French Revolution.
Yes, a time of great upheaval. And he produced a list of what he called 55 simple substances. He tried to categorize them into metals, nonmetals, and gases like oxygen. It was a start. It was basically a laundry list. He was just taking inventory of the universe as he knew it.
But he didn't really see the underlying pattern connecting them yet.
Not quite. That started to emerge a little bit later. In 1817, a German chemist named Johann Dobereiner started seeing, well, ghosts in the data.
This is the triad theory, right?
Exactly. The rule of threes. He noticed that certain elements could be grouped in threes triads where they shared very similar properties.
Like a family.
A little chemical family. For example, he saw that lithium, sodium, and potassium all reacted in almost the exact same way with water. They were clearly related.
And that's a huge clue. It told scientists that the elements weren't just a random collection of stuff.
Right. It meant there was an underlying system, a rhythm, a deep logic to it all. This encouraged the hunt for missing elements to complete other families that seemed incomplete.
Which sets the stage perfectly for the heavy hitter,
Mm.
the father of the modern table, Dmitry Mendeleev.
1869, the Russian chemist with the magnificent chaotic beard. What Mendeleev did was, it was just brilliant. He apparently wrote the properties of all the known elements on individual index cards.
Like playing cards.
Exactly. And he started arranging them on his desk, over and over. He was playing solitaire with the fundamental building blocks of the universe.
How did he organize them? What was his system?
He did two things. First, he grouped them by repeating patterns in their chemical properties, like Dobereiner did. And second, he ordered them by their atomic mass, basically, their weight.
But here is where it gets really, really interesting. He didn't just list what he knew. He was confident enough to leave blank spaces.
That is the stroke of genius. That is the aha moment that changes everything. He's laying out his cards, and he sees the pattern. He sees a family of elements, and he realizes, wait, there should be an element right here to continue this family's pattern, but we haven't found it yet.
So instead of just forcing the next known element into that spot and breaking his pattern,
He just left a gap. He effectively predicted the future discovery of new elements based entirely on the behavior of their neighbors.
and he didn't just predict their existence.
No, this is the really cool part. He predicted their properties. He predicted elements like gallium and germanium before anyone had ever seen them. He said, when you find the element that fits in this space, it will weigh about this much, it will have this melting point, and it will react in this way.
And he was right.
And years later, when they were discovered, he was almost perfectly right. It was an incredible confirmation of his theory.
That is the definition of a good scientific theory, isn't it? It has to predict the unknown.
It does. But there was one slight problem, a few little wrinkles. Mendeleev organized by atomic mass by weight, and for the most part, that worked. But there were a few spots on his table where, to keep the families together, he had to put a heavier element before a lighter one.
So the pattern broke if you strictly followed the weight.
Exactly. Some elements seemed to be in the wrong order, and no one knew why.
It wasn't until 1913 that a British physicist named Henry Moseley finally fixed the map.
And this connects all the way back to the protons we were talking about at the beginning.
How so?
Moseley was working with X-rays, and he discovered the concept of the atomic number. He realized the true organizing principle of the elements wasn't their weight, it was the number of protons in their nucleus.
Ah, so that was the real ID number.
That was the real ID number. When he reorganized the entire table by the number of protons, everything clicked into place perfectly. Those little anomalies in Mendeleev's table made perfect sense. The weight was just a side effect. The proton count was the real fundamental ordering principle.
So when we look at the periodic table today, we are really looking at Moseley's refinement of Mendeleev's brilliant vision.
Exactly. And to read that map today, you just need to know two simple terms: periods and groups.
Periods are the rows going across.
Yes. The horizontal rows are the periods. All the elements in the same row have the same number of electron shells. So as you go down the table from one period to the next, the atoms get physically bigger because they're adding more layers of shells, like an onion.
And the groups are the columns going up and down.
Correct. The columns are the groups, and this is the important one. Elements in the same column have the same number of electrons in their outermost shell.
And because that outer shell drives all the chemistry.
It means that elements in the same group behave very, very similarly. They are a true chemical family.
Which is a perfect transition. Let's
Yeah.
meet some of these families. And we have to start at the very beginning. Top left corner, box number 1, hydrogen.
Hydrogen, the solitary star, atomic number 1.
It really is the simplest thing in the entire universe.
It is one proton, one electron. That's it. There's nothing less you can have and still be matter. And because it's so simple, it is absolutely everywhere.
The most common thing there is.
By a huge margin, it is the most abundant element in the universe. Something like 75% of all the visible matter in the universe is hydrogen.
We mentioned the Crab Nebula earlier. That's basically just a giant hydrogen cloud, isn't it?
Yes. Nebulas, like the Carina Nebula and the Crab Nebula, are these vast, beautiful clouds of hydrogen gas and a little bit of dust. They are stellar nurseries. They are literally where stars are born.
And stars themselves, like our own sun.
They are just vast, vast balls of seething, hot hydrogen gas.
So the light hitting my face when I walk outside on a sunny day, that's just hydrogen doing its thing.
That is the energy being released from hydrogen atoms being crushed together to form helium. It's nuclear fusion. That process is the engine of the stars.
And it's the origin of everything else.
It's the origin of everything else. All the heavier elements we're going to talk about. The carbon in your hand, the iron in your blood, the gold in a ring. They all started out as hydrogen atoms fusing together in the hearts of stars that lived and died billions of years ago. Hydrogen is the grandfather of the entire periodic table.
But it's not just out there in space. We use it here on Earth for some pretty intense stuff.
Oh, we do. Liquid hydrogen is incredibly powerful rocket fuel.
How does that work?
You combine it with liquid oxygen, and you get a massive, massive release of energy. And the best part is the byproduct is just water, H2O. That's what propels rockets into orbit. It's high-efficiency, clean power.
But then, in a very weird twist, it's also in my fridge.
Laughs.
Yes, hydrogen is used in the food industry. If you look at the ingredients for margarine or many shortenings, It uses hydrogen.
How?
It's a process called hydrogenation. They basically blast liquid vegetable oils with hydrogen gas, which makes them solidify at room temperature. It's a thickening agent.
From rocket fuel to toast? That is some serious range.
It's incredibly versatile.
Right.
And we are looking at it for future tech, too. Hydrogen fuel cells for cars are a huge area of research.
Because they're so clean, right.
Exactly. The exhaust from a hydrogen-powered car is just water vapor, nothing else.
I saw a little note in the research that said hydrogen glows purple.
It does, yeah. If you take a glass sphere filled with pure hydrogen gas and you run an electric current through it, it gives off this beautiful, eerie purple glow.
A purple, rocket-fueling, margarine-making star gas. Not a bad start to the list of characters.
Not bad at all.
Okay, let's move down that first column. Group 1, the alkali metals.
Ah. Now we are entering the danger zone.
These are the famously reactive ones. Highly, highly reactive. This group includes lithium, sodium, potassium, and then the heavier ones, rubidium, cesium, and francium.
So why are they so reactive? What is the psychology of an alkali metal? What's going on with their electrons?
It goes right back to those electron shells we talked about. All of these elements have exactly one single, lonely electron in their outer shell.
Just one.
Just one. And atoms hate that. For reasons of quantum stability, they want a full outer shell. It's like having a collection that is missing one single piece, or having one extra piece that ruins the whole symmetry. They are absolutely desperate to get rid of that one extra electron.
So they're aggressive about giving it away.
Extremely. They are walking around the chemical world with a free electron to a good home sign. They will try to bond with almost anything to offload that electron and get down to a nice, stable, full shell underneath.
Which means you can't just find a nugget of pure sodium lying on the ground.
Never. Not in a billion years. They are always found in compounds, locked up with other elements. If you do manage to refine them into their pure metallic forms in a lab, you have to store them under mineral oil.
Why oil? What does that do?
It just keeps the air away. If they touch the oxygen or water vapor in the air, they tarnish instantly. If they touch liquid water, whoa.
It's showtime.
It's showtime. They can burst into flames. The reaction with water is so fast that it releases hydrogen gas and a ton of heat, which then ignites the hydrogen. It's a little explosion.
I remember seeing videos of this in school. The teacher drops a tiny piece of sodium in a beaker of water.
And it skitters around the surface like a possessed hockey puck, fizzing and popping.
Yeah. And physically, they are very weird metals. They're not what you'd expect.
Not at all. They are shiny and silvery when you first cut them, but they are incredibly soft. You can cut a block of pure sodium with a butter knife. It has the consistency of like cold butter or a hard cheese.
Let's look at the specific characters in this very dramatic family. Starting at the top with lithium.
Lithium, atomic number 3. It's the lightest of all metals. It's so light, in fact, that it floats on water.
While reacting with it, which is just a chaotic image. Floating, fizzing fire.
It's a great image, yeah. And we all know this one from our pockets and our driveways.
Batteries.
Batteries. Lithium-ion batteries power our phones, our laptops, our electric cars. It's become a crucial element for modern life because it's so light and it holds an electrical charge so well.
Where do we find it in nature?
Usually in brine pools and salt layers left behind by ancient dried-up seas. The largest deposits are in places like the salt flats of Bolivia and Chile, the lithium triangle.
And here's a fun fact. If you burn it, the flame is what color?
A deep, beautiful crimson red.
Next up is sodium. This is the big one for my salt shaker.
Sodium, or Na. It's the most common alkali metal in the Earth's crust, and historically it's been hugely important. The ancient Egyptians used a sodium compound called natron to mummify their pharaohs.
Because it dries things out.
It's a powerful desiccant. It pulls all the water out of the tissues, which is key to preservation.
Speaking of natron, we have to talk about Lake Natron in Tanzania. This was the most terrifying, surreal thing in the reading material.
It is a truly surreal place. Lake Natron is this body of water filled with natural sodium salts, mostly sodium carbonate, that gets washed out from the volcanic rocks of the nearby Great Rift Valley.
And the water is incredibly alkaline.
Unbelievably so. It's more alkaline than baking soda. It can have a pH of over 10, and it's very hot.
And it's red. It looks red in the photos.
It turns this deep blood red because of a specific type of salt-loving bacteria that thrives in that harsh, salty water. But here's the Medusa part.
Right.
If animals, usually birds, fall into the lake and die, the sodium salts in the water coat their bodies. It preserves them. When they eventually wash up on the shore and dry out, they look like they have been turned to stone.
Like little statues of birds and bats.
Perfectly preserved, calcified statues. It's haunting. It looks like a scene from a fantasy novel, but it's just chemistry, the work of sodium.
And yet on the flip side, sodium is also the brilliant yellow in fireworks.
Yes, that's the duality of it. You have this Medusa Lake on one hand and then a fun, celebratory firework display on the other. If you see that bright, distinct yellow on a firework, that's burning sodium.
Okay, moving down the list, potassium.
Potassium, or K, this one is absolutely vital for us. Your nerves and your muscles need potassium ions to fire correctly.
So this is why people tell you to eat bananas.
Bananas, avocados, sweet potatoes, yeah. They're rich in potassium. Without it, your heart would literally stop. And if you burn it, it has a beautiful lilac flame, a light, delicate purple.
Then we get into the rarer ones, rubidium.
Rubidium, RPV. It was named after the Latin word for red because of its deep red flame color. It's much rarer. It's used in things like night vision goggles because it has a special reaction to light.
And then cesium.
Now we are getting heavy and extremely dangerous. Cesium is the most reactive metal on the entire planet.
So more reactive than sodium.
Much more. It will explode violently on contact with just air. Not even water. Just the oxygen in the air is enough. It also has such a low melting point that it would melt in your hand on a warm day.
What on earth do we do with something that volatile?
We use it to tell time.
Of course we do. That seems logical.
Cesium atoms have a special property. They vibrate or oscillate at an incredibly precise and unvarying frequency. We've harnessed that consistency in what we call atomic clocks.
And these are the most accurate clocks in the world.
The most accurate timepieces humanity has ever invented. They are so precise that they define what a second actually is for the rest of the world. Our entire GPS system depends on the timing of cesium clocks.
And finally, we have the ghost of the group, francium.
Francium is fascinating because it barely exists. It was discovered in 1939, making it the last element to be found in nature rather than created in a lab.
And it's radioactive.
Highly radioactive. Its atoms only last for a few minutes before they decay and fall apart into something else.
The source material said something incredible about the largest sample ever collected.
Yes, in 2012, a team of researchers managed to trap about 1 million atoms of francium together in a magnetic field.
1 million atoms. I mean, that sounds like a lot, but
It is microscopically, unimaginably tiny. You couldn't see it with the naked eye. That's how rare francium is. At any given moment, there's probably less than a single ounce of francium in the entire crust of the Earth. It just appears and disappears like a ghost.
So that's group one, the explosive dramatic family. Let's move one column to the right on the table. Group two, the alkaline earth metals.
Okay, these are the earths. Historically, their minerals, their oxides, were called earths because they don't dissolve easily in water and they don't burn. This group includes beryllium, magnesium, calcium, strontium, barium, and radium.
Are they as crazy and reactive as group one?
Not quite. They're still reactive, but they're a step down in intensity. They have
No.
2 electrons in their outer shell that they want to get rid of.
Still trying to offload them, but not as desperately.
Exactly. They are still shiny and silvery, and most of them are soft, though they tend to be more brittle than the alkali metals.
Let's spotlight a few. Magnesium seems like a favorite for demonstrations.
Oh, magnesium is spectacular because of how it burns. It produces this brilliant, blindingly bright white flame. It's so bright you're not supposed to look directly at it.
That's the white sparkle in fireworks, though.
That's it, but it's also structurally very useful. We mix it with other metals like aluminum to make strong, lightweight alloys. You hear about mag wheels on cars.
Right.
It adds strength but keeps things very light. It's also in medicine. Magnesium carbonate is the main ingredient in many indigestion remedies. It neutralizes stomach acid.
And then there's calcium.
Yeah.
This is a structural element of, well, us.
Right. It's the most common alkaline earth metal in the human body. It's the callow in your bones and teeth. But then you look at the planet. Seashells, the fossilized shells of ammonites, limestone cliffs, the Great Sphinx. That's all calcium carbonate.
Gypsum, too, like the chalk we used in school.
Yes. Gypsum is a calcium sulfate mineral. So whether it's your own skeleton or the White Cliffs of Dover, it's calcium holding it all up. It really is the architectural element of both biology and geology.
Then you have the oddball of the group, beryllium.
Beryllium really breaks the soft metal rule of the first 2 groups. It's hard and tough.
Well,
But its real superpower is that it doesn't change shape when it gets hot or cold. It has incredible thermal stability.
that's very stable.
Extremely stable. That makes it perfect for things that go through intense friction and heat but need to maintain their exact shape, like parts for high-speed aircraft and missiles.
The James Webb Space Telescope is another example.
A perfect example. The massive mirrors on the James Webb are made of beryllium coated in a thin layer of gold because they need to hold their precise curved shape perfectly in the freezing cold of deep space to focus light properly.
Strontium. I love the name Origin here. This is great.
It's named after a village in Scotland. Strontian. That's where the mineral was first discovered.
A whole village in Scotland gets its own element. That's a serious claim to fame.
It really is. Strontium is used to create deep, rich red colors in fireworks. It's also, oddly enough, used in toothpaste for sensitive teeth. It helps block the little nerve channels in your teeth.
And it has a radioactive use, too.
It does. A radioactive form is used in something called a radioisotope thermoelectric generator, which is basically a nuclear battery. They use them to provide steady electricity in very remote places like Arctic research stations or unmanned lighthouses.
And barium and radium to round out the group.
Barium is very heavy. It's great at blocking radiation, which is why you have to swallow a barium meal before certain x-rays.
Right, the barium milkshake.
That lovely chalky stuff, yeah. It coats your digestive tract so it shows up clearly on the x-ray scan because it blocks the x-rays from passing through.
And radium.
Radium is the famous one, discovered by Marie and Pierre Curie. They found it in uranium ores. It's highly, highly radioactive. It famously glows with a faint green light in the dark.
And this has a really tragic history, doesn't it?
It does. In the early 20th century, before we really understood the dangers of radiation poisoning, people thought it was a miracle cure-all. They put it in water, in chocolate, in face creams.
The Radian girls.
And the radium girls, the young women who painted watch dials with radium paint so they would glow, they suffered terribly from radiation poisoning. It's a very somber reminder that these elements have powerful properties that can hurt us deeply if we don't understand and respect them.
Okay, so we have done the two very reactive columns on the left side of the table. Now we hit the massive block right in the middle, the transition metals.
The builders. This is the largest single collection of elements, 38 of them in this block.
And these are what most people would typically think of when they hear the word metal, right?
Generally, yes. Hard, dense, high melting points, high boiling points. They conduct heat and electricity really well. This is the industrial backbone of our entire civilization.
This is where we get into heavy industry, smelting and alloys.
Right. You extract these from ores by melting them in furnaces at red-hot temperatures. And you almost always mix them to make alloys. Steel, brass, bronze. These are all mixtures of transition metals designed to have specific properties.
One thing the research highlighted that I didn't expect was color. The transition metals are very colorful.
The metals themselves are usually that familial silvery or gray color, but their compounds are extremely colorful. They absorb different wavelengths of light because of the way their electrons are arranged, which is a bit more complex than in the other groups.
The Rainbow Mountains in China were the big example.
What an incredible visual. It's a geological park where the mountains have these vibrant stripes of red and yellow rock. The red is just iron oxide rust. The yellow is iron sulfide. It's geology being painted by transition metal chemistry.
And this goes way back in art history, too, to cave paintings.
Oh, absolutely. 15,000 years ago in caves like Altamira in Spain, early humans were using ochre, which is just a mix of iron oxide and clay, to paint those incredible red bowls on the walls. For centuries, the element cobalt has been used to create that deep, beautiful blue in fine china and stained glass. Without transition metals, our world would be a very drab, gray place.
Let's run through the heavy hitters in this group. You have to start with iron.
You cannot talk about Earth without talking about iron. It makes up about 35% of the entire mass of our planet.
35%, that seems incredibly high.
Well, most of it is in the core. The very center of our planet is a hot, spinning ball of molten iron and nickel. And that spinning iron is what creates the Earth's magnetic field, which protects all of us from harmful solar radiation.
So iron is our planetary shield.
It is, and it sustains us on a personal level, too. Hemoglobin, the molecule that transports oxygen in your blood, works because it has an iron atom right at its center. Your blood is red, essentially, because of rusted iron.
Titanium. That feels like the modern metal.
It really is. It's as tough as steel, but it's much, much lighter. It's the ultimate aerospace metal. A modern super jumbo jet, like an Airbus A380, has about 77 tons of titanium in its structure.
Wow.
It's also biocompatible, which means our bodies don't reject it. That's why we use it for things like hip replacements and dental implants.
Vanadium. That sounds like a metal from a sci-fi movie.
It acts like one. It's an additive. You put a tiny bit of vanadium into steel, and it makes it super tough. Ancient Indian swordsmiths making Damascus steel unknowingly used ores rich in vanadium, which made their blades legendary for being sharper and stronger than anything else at the time.
And what do we use it for now?
Today, we use it in the walls of nuclear fusion reactors because it doesn't warp or become brittle under extreme heat and radiation.
Chromium.
The shiny one, the chrome, on a classic car bumper. Stainless steel doesn't rust because it has chromium mixed in. But in nature, in gemstones, tiny amounts of chromium are responsible for the deep red color of rubies and the brilliant green of emeralds.
Wait. The same metal that makes car bumpers shiny also makes rubies red.
Chemistry is wild, isn't it? It's all about how the individual chromium atoms sit inside the crystal structure of the gem. It just bends the light differently depending on its surroundings.
Manganese?
On its own, it's a dull, gray, brittle metal. Not very useful, but, like vanadium, it's a crucial hardening agent for steel. The armor plating on a tank is manganese steel. It's the tough guy of the group.
Okay, cobalt. I teased this earlier. The name origin is fantastic.
Yes, it comes from the German word kobold, which means goblin or mischievous spirit.
A goblin. Why?
Well, medieval German miners would find this ore in the mountains. It looked a lot like silver ore, but when they tried to smelt it, it didn't give them any silver and it released poisonous fumes. Arsenic is usually found with it. So they blamed mischievous spirits in the mines for tricking them and poisoning them, the kobolds.
The goblins ruined the silver.
Exactly, and the name stuck. Cobalt. Magnets and coins. The U.S. nickel, the 5-cent coin, is actually an alloy of copper and nickel. The natural ores of nickel are often this beautiful pale green color, a mineral called garnierite.
And we can't forget the so-called coinage metals. Copper, silver, and gold.
The classics. These were known to ancient humans because, unlike most metals, you can find them in their pure, native form just lying on the ground.
Right.
Copper is used for electrical wires because it conducts electricity so well. Silver is actually the single best conductor of all the elements, but it's far too expensive to wire your house with it.
And gold.
The king. It's rare, it's beautiful, and it's almost completely unreactive. It stays shiny and perfect forever. That perceived immortality is why we valued it for currency and jewelry for thousands of years.
And let's wrap the group with zinc.
Ancient medicine. The calamine lotion you put on bug bites is mostly zinc oxide. It soothes itches. It's also used to galvanize steel. You coat the steel in a layer of zinc to protect it from rusting.
It's amazing how these range from tank armor to anti-itch lotion to the coins in our pockets.
That's the versatility of the transition block. They build our world, they protect us, they power our technology, and they even heal us.
I want to briefly touch on the states of matter before we wrap up.
Yeah.
We've been talking about all these elements as solids, liquids, gases.
Right. Every element has a standard state at what we call room temperature, which is generally set at 20 degrees Celsius or about 68 Fahrenheit.
And most of them are solid.
The vast majority are. Gold, iron, bismuth, carbon, they're all solids. The atoms are locked into a tight, vibrating pattern.
So are liquid.
Very few, actually, at that temperature. Only two. Mercury, which is that famous liquid, metal-heavy, silvery, alien-looking stuff, and bromine, which is a nasty, fuming, reddish-brown liquid.
And then the gases.
Chlorine, hydrogen, oxygen, helium, nitrogen. Their atoms are completely dispersed, just zooming around free of each other, filling whatever container they're in.
And then we have the difference between a compound and a mixture. This is Chemistry 101, but it's a really important distinction.
It's a crucial distinction, yeah. A compound is when elements bond together chemically to make a completely new substance, like the copper nitrate we saw in the sources. You can't just pick the copper atoms out. You need another chemical reaction to separate them.
The salt on my fries? Sodium chloride? That's a compound.
A perfect example. It's nothing like explosive sodium metal or poisonous chlorine gas. It's a brand new thing.
And a mixture.
A mixture is just physical, like a salad or an alloy. Brass is a physical mixture of copper and zinc atoms. They are just stirred together, but they haven't chemically bonded to make a new molecule. Rocks are often mixtures of different minerals.
So we have taken quite a tour today, from the lightest gas in the universe, hydrogen, through the explosive alkalis, the structural earth metals, and the industrial transition metals.
It's a journey from the birth of stars to the steel in our skyscrapers.
And the blood in our veins.
And the blood in our veins, absolutely.
It really brings it all back to that intro thought. These 118 ingredients are literally it. They make up everything.
Every mountain, every ocean, every distant star, and every single person listening to this right now.
So here's a final thought to leave you with. If we are made of these elements, carbon, oxygen, iron, and all of these elements heavier than hydrogen, were forged inside stars that lived and died billions of years ago.
Then we are, in a very real sense, recycled material.
We are. We are just the current arrangement of atoms that have been around for eons, traveling across the cosmos. Does that mean we are technically just animated stardust?
I think both scientifically and poetically, the answer has to be yes. We are the universe, built from its own ashes, becoming aware of itself.
Something to think about the next time you look up at the night sky or look in the mirror, or just shake some salt on your fries. That salt is sodium from the earth and chlorine from the gas, and you are the carbon-based life form built from stardust, enjoying it.
It connects us to everything. It's a beautiful thought.
Thanks for diving deep with us today. We'll see you on the next one.
Goodbye.